Hello everybody, so today I will talk about the design Ticketmaster question game. Today I will, talk about these three topics again. Actually, I talked about this yesterday, but for my own practice sake, I'd like to repeat what I explained again today. This is the function requirement, non-function requirement, and API designs. So I'd like to quickly draw the high-level architecture again, and then I will work on these topics today. So firstly, there is a user who'd like to design, books a ticket. And these users makes the request. So I will take a look at the first API, search event. So I will go so quickly here because I've already explained. The reason why I'm doing it again is for my practice, and also I using my another laptop, so I actually don't have the architecture, you know, chart I drew yesterday. So that's why I write it again. So the request should go through API gateway. So API gateway is used for the routing to the backend microservices and also authentication and sometimes write parameter. So when user makes a request, it hits the API gateway first, and then it goes to the backend service. Because we're talking about the search event API, I will create the search service here. And we'd like to search the event, and event should be obviously in the main DB. So I put it here. So I use PostgreSQL. If necessary, I will change it, but yeah, it works in this case actually. So in this event DB, we store event data. Yeah, something like this. And also, as I said, okay, so what I'd like to know is all about event for now. So this is good enough. So search service should query the event from main DB. But as I talked before, um, because we have to search by the keyword, PostgreSQL is not a good fit here. Because if I'd like to use the query, use a search with the keyword with PostgreSQL, we have to use like where keyword is something like. So we have to use the like clause. And it has to scan all the column data in the table, so it takes a long time. The query becomes so slow. So instead, I will use the Elasticsearch. And Elasticsearch, this should not be used as the main DB. This should be a kind of, data which is derived from the main DB. So for this, I will use a CDC. And search service should make the query to the Elasticsearch. So now Elasticsearch has the inverted index from the each keyword in the description to the event ID, and also it has the mapping from the, it internally has the geospatial index. So from the area search, it can quickly find the event which are in the specified area, and also, what is it? Yeah, date. Okay, date range. Yeah, it's also possible. So that being said, so this is how the search event works. And now I will talk about the get event. So let's say this, yeah, I will separate search and, you know, get event service because I direct them to, scale independently. Because, for example, let's say Taylor Swift makes the announcement of the concert, and let's say that link is sent to the users via the, let's say, email for the fan club members of the Taylor Swift. In that case, only the get event API should have the spike. So that's why these actually have the different scenarios for the traffic. I mean, when the spike happens for the traffic. So that's why I will use the another microservice here. But what it does is fetches the event from the main DB, and because okay, and we use the primary key on the event ID so that the event can be fetched quickly from the PostgreSQL. Okay, next, get ticket. So for this get ticket, this is about the seat available or not. So actually, more accurately saying, this is get seats, maybe. But as I said before, I will use event seat. So this is the seat recode per event. So this is different from the physical seat because each venue has the physical seat. But for example, let's say there is a concert in the stadium. There are some seats which are not used as for the audience because it's used for the stage. So from the physical seat for each event seat record are created. And as I said before, we'd like to use the kind of two-phase booking. So I mean, the seat is firstly reserved and then it is booked. So we use the state machine from available to reserved to booked. So we have to, control it. So as I said in the last video, I will use the optimistic locking here. So we use the reserved by user ID and reserved until. And as I said, version key for optimistic lock. Okay, so this is something we have to put here. Then for seat query, get ticket query, you know, all the seat in the event should be returned, or maybe area of the seat. So I would say get event API here. So get event query here, and get seat query here. Okay, then we have the purchase ticket API. So what we talked before is that we use the third-party payment system for the credit card because we don't want to save the credit card information in the backend, because first to do that we have to comply with the PCI regulation, which is a very hard and challenging for so that's why we use the third-party payment system like Stripe here. So as I said, because we don't access the credit card, what happens is that in the checkout page, the iframe, a kind of nested frame of the payment credit card input page is displayed. Then user input it, and that request is sent directly to the Stripe. So in this way, now credit card information is saved. Then in exchange of that, the token is returned. So this is a token which identifies the credit card in the payment system. And now what happens is that when for the payment API, so firstly, before purchasing the ticket has to be secured. So even it is secured by that user to make the request, and reserved by is updated with now plus 10 minutes, and reserved by is secured by the user ID, and reserved until should be updated with now plus 10 minutes. So that's what happens in purchase ticket API, or I should say reserved ticket API. Yeah, and then for the payment API, now user makes a request with the seat ID to purchase and also the payment token. And now there is a booking service. So booking service should do something I talked first with this API in this way. And then I'm talking about the payment service. So payment service should request a second request, which is as I said, request specifies the payment token, seat ID, also user ID, which can be extracted from the session token, and the request is hit onto the payment service. And now this payment service makes a request to the Stripe. So this specifies the obviously token of the credit card and also the seat ID as the metadata. Yeah. And what happens is that this third-party payment system makes the credit card payment with the card network. Then it makes the webhook. It calls our system with webhook. So I create another server here, payment webhook receiver or something. And Stripe makes the request here, and our service updates the here. Now this updates booking record. And that's it. So here we specify seat ID, user ID, and something like the more information like booked at, or maybe we would like to get when ticket was issued or something like that. So this is all about the payment flow. Okay. Okay, so from here, I will talk about today's topics. So number one, I will talk about the delay of the web from payment system. So let's say the ticket is reserved at 10 a.m. and it should be paid. The payment should be done until 10 p.m., 10 minutes later. And let's say user tries to pay for it at 10 p.m., 9 minutes, 95 seconds. In that case, yes, he can pay. But however, what happens is that maybe payment webhook receiver receives the webhook request like later than 10 minutes. So it can be the problem. So before discussing that, I actually found something I have to clarify a little bit. So booking service reserves the ticket, but of course here. With this payment service, this has to confirm if he can pay for this ticket still. So this calls the main DB PostgreSQL event seed recode, and take a look at this and confirms that reserved by is exactly the user who's trying to pay for it, and also reserved until is now or before. That validation is necessary here. So that about the validation. What happens first? Okay, so that being said, when user tries to pay, makes the payment 9 minutes 90 seconds, 9 minutes 59 seconds later, this validation passes. However, after that, when 10 minutes has passed, this ticket becomes now available. So because reserved by is, so reserved until is, yeah, the past timestamp. But wait, so what I'm thinking now is, how can I make sure that other use? So what should I do if the seat is booked? Sorry, maybe I need here, this one here. Booked by, booked at. Yeah, so I would use this timestamp. So when the booking is created, this payment webhook service makes a query to DB and update this, and also create booking record. Those two operations should be done in the same transaction to keep that misty. But that being said, the problem here is the delay of the webhook. So if webhook request is received at 10 minutes 10 seconds later, for that 10 seconds, now other user can reserve the same seat. And what happens is that user can make the request, makes the payment, but in the end, when that second user's webhook is sent to this server, and when this tries to create the booking recode, it fails because it's the second booking record for the same seat, and then the second user, should be made the refund, and even though he could pay for the ticket, the booking fails and his money is refunded to the credit card. This is a bad experience. So what I can do is, instead of managing the deadline for payment, and in one column, we use two things. So we use reserved until and reserved at. Yeah. Or maybe I can use purchase until. Yeah, of course I need the reserved at, but also maybe we need reserved until and purchase until. So what I mean here is, reserved until is the exact timestamp when user reserves the ticket, and reserved until is at the same time set with reserved at plus 10 minutes, and purchase until is set with reserved at plus 10 minutes 10 seconds or something, a little delta here, which is for the delay of the webhook. So in this way, the scenario I talked is completely covered. Okay. Yeah, just to be clear, these are redundant actually, but I think it's a good idea that we put, create separate columns for this. Reserved until, this can be derived by reserved at plus 10 minutes, but instead I create this separate column for the debuggability. And yeah, it makes it much easier to see what's happening inside. Okay, I will talk about the second topic, scalability. So as I wrote here, scalability, 100 million data users, 100K event per day, and 100 times spike. And I will talk about this from two perspectives. Number one is throughput. Number two is data size. So let me start with the throughput. So 100 million data users, 100K event per day, 100 times spike. I will make it converted into the request per sec. So let's assume each user takes a look at 10 pages per day. So in that case, 100 million users in a day, each of them takes a look at 10 pages, and one day is around 10 to the 5 seconds per day. So this is the request per sec for viewing, not the booking. So this is 10 to the 8 then times 10 by 10 to the 5. So this is 10 to the 4, so 10K requests per sec. Is this correct? Yeah. Okay. So 10K requests per sec. This is not some big number, I think. So now, oh, no, but there is a spike. So we have to assume that this becomes 100 times. So that should be 1 million requests per sec when spike. Okay, so now I will talk about the booking. So let's say there are 100 million daily users, and let's say maybe 1% of them makes a request, makes a booking. So with this, in this case, with the same explanation, sorry, with same mathematics, we get 10 requests per sec. And when there is a spike, sorry, this is wrong maybe. Yeah, this is correct. This is 1K requests per sec. Okay, so this is it. So yeah, maybe 1% is little too small, too little. Let's say there is 10% of the user who makes the booking. In that case, there should be 100 requests per sec and 10K requests per sec. Okay, so this is the throughput we have to handle here. So let's take a look. So for API gateway, okay, sorry. So I will talk about the 1 million requests per sec viewing event when there is a spike. So API gateway, this is fine because internally this is a fleet of servers, so this can horizontally scale internally. And for search event, for server, we use the horizontal scaling. So typically, one EC2 instance can handle around 1,000 requests per sec if the request itself is quite simple. So yeah, we can use the horizontal scaling. So if we'd like to handle 1 million requests per sec, maybe we need 1,000 servers, but this is completely fine because we can use AWS auto scaling, so it automatically scales according to the traffic. Maybe amount, or maybe from the CPU memory usage of the server. Okay, and now we make the request to Elasticsearch, but as I said before, for search, there shouldn't be so much spike actually, because typically what happens when there is a spike on the viewing event, for the event, reading is from the link, not from the search. So I assume there should be 10K requests per sec. Yes, in that case, Elasticsearch is can handle that amount of request. Maybe we can use just one or two read replicas kind of in Elasticsearch to handle it. Okay, so in this way, search request could be handled. Now I will talk about the event viewing. Completely the same way, we can auto-scale the event service and use the read replicas for the PostgreSQL. So this is good. Yeah, because we, talked that for the read, aside from booking, we accept the eventual consistency, so read replicas can be used. Okay, so now we'll talk about the booking. So when there is a spike in the booking, what happens is that there's so many requests coming to booking service and then payment service. So for booking service, I can auto scale, but for the query to DB, this is a kind of pain point, because when we write something to the DB, basically it is handled by the primary node. It obviously can't be handled by the read replicas. So the problem here is if 10 kilobits per sec can be handled by a single reader node, primary node. And this is possible. 10 kilobits per sec can be handled by the PostgreSQL. So this is good. But if this is not possible, I will use a sharding. So I will use a sharding by the event ID and split the data across multiple DB. Yeah, because each event can be thought to be independent, so it's totally fine. Okay, so for the payment, yeah, same. I can auto scale the payment service, and also I can auto scale the webhook receiver, so it's totally fine. Good. So now I've talked about the scalability, about the throughput. So from here, I will talk about the data size. So here I can find 100K event per day. So this means that we have event table and also event seed table and also booking table. So event table is exactly 100K records per day, and let's say each event record has 100 byte data size. In that case, it becomes 1 gigabyte, 10 gigabyte per day. So yearly, this becomes 3 terabyte per day. Sorry, year. Yeah, this is small enough because nowadays, let's say AWS Aurora can store 256 terabyte of data. So it takes 80 years to, run out of the storage. So this is completely handleable with PostgreSQL. However, for seat record and booking record, this becomes quite huge because for each event, there are maybe 10,000 seats or something. For example, for Studium, there should be around 50K. seat. So let's say on average they're 10K. Seat per day, and also booking per day. So in this case, this becomes 1,000,000,000 times 100, which is 100 terabyte per day. Yes. So which is in year, it becomes 30 petabyte. Yeah. So this is quite huge. So I have to think how I can handle this. So the quick idea here is use the sharding, as I said. Yeah. Or yes, I think I can use the sharding, but sharding comes with a kind of complexity. So the approach I will take is I split the data into two databases, and one is EventDB. So this is relatively small, so we don't need the sharding. And the other is seat and booking DB. Yeah, I call it seat DB, and I call this EventDB. So for this one, yeah, I will do the sharding by event ID. Okay, so that's what I would do here. Because the good thing is payment webhook receiver has to make the query to the single database, so the transaction still works. Okay, so this is it. And also, something I can say is, even though we store the event in the seat data and booking data in the single, I should say, each shard, after the event is finished, this data doesn't have to be in PostgreSQL. For event seed, maybe we can delete this, or maybe store it in the S3 cold storage. And same for booking data. So the only time when user needs the booking data is, I guess, when he looks at the past booking page. So the access pattern here becomes, for each user, he'd like to fetch all the past bookings. So maybe the idea is we can store the bookings for the same user in the same file in S3. In that way, when user try to fetch the booking list, internally we just have to fetch only one S3 object. So that's something I can do. And obviously we can use the Glacier, S3 Glacier, right, cold storage, which takes more time to fetch, but it costs cheaper, so we can use it for the cost efficiency. Okay, so now I will talk about the last topic, waiting queue. So I will be more, firstly, I will talk the specification of the waiting queue. The firstly, the problem here is when there are so many users who'd like to, so let's say Taylor Swift concert ticket is bookable from 1 p.m. And at 1 p.m., there are so many users visiting the booking page, and so many users see the seat maps. Then they they select the seat and try to reserve the seat. However, because there's so many users who are opening the seat page, um, even though in UI it is available, when he clicks it, that seat may be taken by another user. In that case, he has to choose another seat, and maybe the same thing happens. Then he chooses another seat, the same thing happens. That repeated. So that's a bad experience. So that being said, what I'd like to realize here is, number one, seat mapping should be updated every time the seat is reserved. Maybe not, of course, maybe not every time, but maybe like every 10 seconds. And more importantly, we'd like to limit the number of users who can go into the seat selection page. Obviously, we don't want 1 million users comes into the you know seat selection page. So the concept of waiting queue is, let's limit the users who can go into the seat selection page to 10,000 users, and let's set the time limit in which that user can book select the seat. Yeah, let's say it's 10 minutes. And then what happens is, after a user makes the booking, or after that user's 10-minute slot is expired, new user can come into the selection page, seat selection page. And those are waiting in the waiting queue before entering the booking page. So that's the concept of waiting queue. So here we need two concepts: waiting queue, and also the kind of user who's users who are in the seat selection page. So we need two data stores here. So for waiting queue, I will use the Redis sorted set. And for and to manage the users who are in the seat selection page, again, I use Redis. Okay, because I'd like to use the TTL, time to read, 10 minutes. So the modification I will make here is, before user comes into the booking service, so let's use this. So let's introduce another service named waiting queue service. So if he'd like to connect to the waiting queue, he'd like to book a ticket, he'd firstly makes a request to this waiting queue service. Maybe we can limit this waiting queue to the popular event, which we can predict. So only for those events, if he'd like to book the seat, his front-end firstly makes a request to waiting queue service. And now what this does is, he pushes the user into the Redis sorted set. So the reason why I use Redis sorted set, not the Kafka, even though this should be the queue, is because yeah. So number one, we'd like to know how many users he has to wait until he can enter the booking room. In Kafka, it is harder to know in which position the message is. But in Redis sorted set, we can fetch it in all login time. And also, maybe there's some user who'd like to cancel the waiting. Samely, in Kafka, deleting the message in the queue is not so easy. But for Redis sorted set, it is possible with all login time. So that's why we use the Redis sorted set. So we add the user to the Redis sorted set. And periodically, this should be moved to the another Redis. So here, this is the Redis, just a set, it's fine. We don't have to sort the users here. But here, we use the TTL. So, okay, wait a minute, so Redis, wait, Q Redis. And for here, we call it booking room. Okay, now, as I said, there should be the periodic job, which moves the user into this. Yeah, sorry. Wait a minute. So this moves the user from waiting queue to the booking room. Okay. Maybe delete users, as I said. And this specifies this has the TTR 10 minutes. So obviously, when we introduce architecture, when user try to book the service, we have to validate that this user is already in the booking room. So I need this API call here. And also, when the booking is done, we'd like to delete that user from Redis set for the waiting users. Wait a minute. Okay, so that was but I think now I can find a little bit of problem. So here, payment webhook receiver makes a request to CDB, and also there is the record from Redis set. But here, we cannot use a transaction because they are not in the same database. But for this delete, I think I can make it best effort because in the end, the user should be deleted with TTL 10 minutes. So instead of introducing the complexity, like using the outbox transaction pattern or something. We just make it best effort here. Okay, so this is it. So yeah. And the thing is, if he'd like to know which position he is in the waiting queue, this waiting queue service can make the query to Redis so they said and know which position he is and return to the user. Oh, and one more thing I forgot to tell is we'd like to update the UI of the user periodically. So I think we can use the WebSocket here. So when there is a when the ticket is reserved here, what I can do is booking service should yeah. Hmm. Maybe okay. So the naive approach, quick up idea is to use the short polling. So user makes the query to book service to get the list of seats every 10 seconds, but it can be quite heavy. Oh no, I think this is possible because we limit the number of users to 10K. So let's say 10K users makes a request to the server every 10 seconds. In that case, it should be 1K requests per sec. It should be completely handleable. And also, we can cache the receipt because user makes a query every 10 seconds. Okay, so my idea here is, let's say we use another Redis here, like seat availability Redis. And there is a process which update this maybe every 10 seconds. And seat availability service should query from this seat available Redis when user actually only 10,000 users who were in the booking room makes a query to seat service. So if okay, so there are 10,000 users who were in the booking page. Those users should make the query to fetch the latest seat maybe every 5 seconds, and it fetches a record from seat availability Redis and returns to the user. And there is another process which periodically, maybe every 5 seconds, um, fetches the seat availability and update seat availability Redis. Okay, so this is my idea. Okay, so that being said, I think I could implement the waiting queue functionality. Yeah, good. So that being said, I finished my today's system design practice. Thank you so much. Bye.